It may be hard to believe, but it was 40 years ago tomorrow that the biggest of big bangs rocked the Pacific Northwest. Luke Burbank takes us back.
44 years since the eruption of Mount St. Helens. It covered the Northwest in clouds of ash. KGW crews were covering the eruption in the air and on the ground that day, seeing and feeling the effects up close.
Mount St. Helens is rumbling, with eruptions predicted up to 3 days in advance. Since February, hundreds of small earthquakes have shaken the ground beneath this iconic Washington volcano, capturing global attention. What's behind this surge in seismic activity? Could another explosive event be on the horizon? Scientists have developed a groundbreaking technique to predict eruptions up to 72 hours ahead. But will this be enough to outmaneuver nature's unpredictability? Discover the secrets of MuskMind. Hit like and subscribe now. The Pacific Northwest Seismic Network has recorded 350-plus quakes beneath the volcano since February, with nearly 95% below magnitude 1, too weak to be felt. The biggest spike came in early June, with 38 quakes in a single week. These tremors originate 4.6 miles beneath the crater, a depth consistent with long-term volcanic patterns. According to USGS scientists, the activity stems from a natural process called recharge, when fresh magma rises from deep within the earth, accumulating in underground reservoirs. This process has been observed at Mount St. Helens and other active volcanoes worldwide. In a recent X, formerly Twitter, update, the USGS explained that magma ascends from 16 miles below before pooling in an upper reservoir 2.5 to 6 miles deep. When magma enters this chamber, it increases pressure and triggers quakes. Despite the elevated activity, the USGS confirms there's no immediate threat of an eruption. Seismologist Seth Moran reassured that fluctuations like these are normal. Mount St. Helens is a geologically active volcano. We've seen similar upticks before, and they don't always lead to eruptions. The last eruption, 2004 to 2008, gave scientists a rare chance to study volcanic processes in real time, advancing monitoring techniques. Back then, quakes spiked to 1 per minute, a stark contrast to the current lower frequency, suggesting today's activity is not yet a warning sign. Moran suggests 2 possible causes: new magma influx into the crust, increasing stress and triggering quakes; gas pressure buildup from leftover magma, possibly setting the stage for future eruptions. If pressure keeps rising, could history repeat itself? Only time will tell. Another earthquake was recently reported near Morton, Washington, adding to the region's seismic activity. This tremor, recorded by the USGS at 7:52 a.m. on November 28th, struck just north of Mount St. Helens and west of Spirit Lake at a depth of 2.2 miles. While unrelated to deeper volcanic activity, it highlights the region's tectonic complexity. The social media account Earthquake Quake Alerts, which compiles seismic data from the USGS, initially reported the quake at a magnitude of 2.3 before the agency revised it to 1.2. Despite the slight uptick in activity, the USGS reassures that there's no cause for concern. These tremors haven't changed the volcano's hazard level or affected monitoring systems tracking ground deformation, gas emissions, and thermal activity. An eruption is not imminent, the agency confirmed. Mount St. Helens remains one of the most closely watched volcanoes in the world, a status solidified by its devastating May 18, 1980, eruption, the largest in U.S. history. That disaster spewed 520 million tons of ash, reshaped the landscape, and took 57 lives, including USGS scientist David Johnston, who radioed his final warning. Vancouver, this is it. His message, though not received in time, was captured by a ham radio operator, preserving a chilling moment in history. Today, advanced technology continuously monitors the volcano's subtle movements. USGS seismologist Seth Moran compares the efforts to placing a blood pressure cuff on Mount St. Helens, detecting even the slightest geological shifts. He explains that the recent seismic activity is part of a natural process called recharge, where magma slowly accumulates beneath the surface. This process can continue for years without triggering an eruption. Between mid-July and October last year, over 400 small quakes, mostly below magnitude 1, were recorded, too weak to be felt. Similar swarms occurred in the 1980s and 90s without leading to an eruption. Scientists rely on indirect evidence, like earthquakes, to assess volcanic behavior. Moran puts it simply. The earthquakes are the symptom. The diagnosis: a recharging volcano. The 1980 eruption was a wake-up call for hazard preparedness, leading to major advances in monitoring. Today's tools, seismic networks, satellite imaging, and gas detection, allow scientists to track changes in real time, ensuring rapid response to any signs of escalation. Despite recent tremors, Mount St. Helens poses no immediate threat. The current activity aligns with previous recharge periods and falls within expected patterns. But what if we could predict its next eruption days in advance? Could this be possible? Let's find out. A team of physicists, geologists, and signal theorists from the University of Granada, Spain, has developed a machine learning algorithm to predict volcanic eruptions, specifically at Mount St. Helens. Their study, published in Frontiers in Earth Science, details how they trained the system using historical eruption data. By recognizing patterns leading up to past events, researchers have made major advances in volcanic prediction technology. For decades, forecasting eruptions has been a major challenge. Scientists monitor seismic activity, gas emissions, and ground deformation, but reliable predictions remain difficult due to the unpredictable nature of volcanoes. Signals that indicate an eruption at one may not apply to another, limiting existing models to a short warning window of just a day or two. To overcome these challenges, the team focused solely on Mount St. Helens. They compiled extensive data, including seismic records from before and during the 1980 eruption, to train their algorithm. The system was designed to detect subtle patterns missed by human researchers, using mathematical models to analyze earthquake signals, pressure buildup, and stored energy, key eruption indicators. After training on multiple past eruptions, the algorithm was tested for accuracy. It achieved a remarkable 95% success rate in predicting eruptions at least 3 days in advance, significantly improving traditional methods that typically offer only 1 or 2 day warnings. This breakthrough could greatly enhance public safety by providing earlier alerts, allowing more time for evacuation and preparation. It also sets the stage for similar predictive tools at other active volcanoes. The study comes at a crucial time, as monitoring teams have reported increased seismic activity and gas emissions at Mount St. Helens, suggesting the volcano may be entering a more active phase. While this doesn't guarantee an imminent eruption, it highlights the need for continuous monitoring and advanced prediction tools. Machine learning is revolutionizing geoscience by uncovering patterns in vast datasets that might otherwise go unnoticed. The success of this algorithm at Mount St. Helens suggests it could be adapted for other volcanoes, improving forecasts worldwide and minimizing disaster impacts. Could the next eruption rival 1980? Despite the volcano's reduced height, an eruption could still be just as explosive. The intensity depends on factors like magma composition, gas content, and pressure buildup, not just the volcano's size. Mount St. Helens is known for its silica-rich andesitic and dacitic magma, which is highly viscous and traps gases. When pressure builds and is suddenly released, it triggers explosive eruptions, as seen in 1980. That eruption, caused by extreme pressure buildup, reshaped the volcano by removing its northern flank in a massive landslide, the largest in recorded history, reducing its height from 9,677 feet to 8,363 feet, and leaving behind a large crater. Despite its reduced size, Mount St. Helens remains highly active. Magma reservoirs beneath the surface continue to recharge, building pressure that could lead to future eruptions. The crater's formation may have made magma ascent easier, increasing the chances of smaller dome-building eruptions and potential explosive events if excessive pressure accumulates. Gas content also plays a key role in the volcano's activity. As magma rises, dissolved gases like water vapor, CO2, and sulfur dioxide expand, sometimes leading to violent eruptions. While the 1980 event was particularly devastating, Mount St. Helens has erupted multiple times over the past 10,000 years, including smaller dome-building eruptions between 2004 and 2008. Eruptions at Mount St. Helens occur in cycles, often separated by decades or centuries. Although no major eruption appears imminent, scientists closely monitor seismic activity, ground deformation, and gas emissions for warning signs. The volcano remains a significant threat, capable of producing another explosive event if conditions align. As for whether Mount St. Helens could trigger nearby eruptions in the Cascade Range, the connection between volcanic activity in the region is complex and remains uncertain. Make sure to subscribe to MuskMind for more intriguing and informative content. Thanks for tuning in.